G'day everyone. We're looking at geometry today. We're continuing on with the discussion of the Great Riddle. So, and specifically looking at geometry, I've got my Good Vibes shirt on because indeed we're talking about vibrations. So, geometry and vibrations. So this is the framework that I use in general to understand this great riddle with these three nested cubes. So what we're looking for is a six-dimensional space. We're trying to create a six-dimensional space that houses three dimensions for space, spatial directions, up, down, front, back, left, right. But then we've got the processes of interaction and consciousness. So we've got before and after. Then we've got growth and decay. So that's got some embodied identity in there as well. And then we've got consciousness over the manifest form. So we end up with these six dimensions to the manifest structure. And what we're going to say, we're going to begin with a bit of science here. So we're going to try and fit these six dimensions into this three nested cubes shape. So this is like, so it's a physics. We're looking for a fundamental physics. And inside here we've got the spark, and then we've got the form, and then the field. So we've got this breathing out and breathing in, this manifestation of this multi-dimensional space with an inside, a form, and an outside, a spark, form, and field. And looking at the structure of waves, there's the way that they break down is can be seen on the guitar. I'll show you in a sec. So this is the half here, and in the middle point here we find the octave. So Pythagoras told us if we halve the wavelength, we double the frequency of the wave, and we get an octave. So the next major subfrequency for any note is if we divide the string into thirds. So here we find the major fifth note. So do, re, mi, fa, so, do, so, do, so. These are major fifths here. And then finally, if we divide the string into five, then we end up with 1, 2, 3, 4, 5 sections. Then on these points, we find the major third. Do, re, mi, do, mi, do, mi. And the first, third, and fifth note in a major scale make up the chord, the major chord. So looking at the guitar, we're just going to be touching the string lightly. So that's the bass note we're using, the D there. You could pick any of them. The D, and then we divide the string in half. Doom, doom. We've got an octave. So, but we're just touching the string here. And we still get the harmonic. We can hear it at the quarter as well. Another octave up. We can hear it at the eighth. I've marked it on here to make it a bit easier. Whoops. Should be able to hear that. One octave up, two octaves up, three octaves up at the half, the quarters, and the eighths. And here we see on this outside circle here, we've got the half, the quarters, and the eighths marked in here. So they're all octaves, but we're saying that this waveform that occurs within every small section, this is equal to, let's call it just 1 for now. And the 1 breaks into half, thirds, and fifths. So those are the octaves, are the only ones I've drawn there. But if we divide the length into 3, we get the major seventh. And it's the same again if we shorten the string to 2/3 the length or 1/3, we get the same, but a different. So if we go this way, That's another octave up, divided into thirds that way. But this harmonic here, and where are we here somewhere? There it is, the third. And then dividing it into 5, we get do, re, mi. It's less easy to smooth out the vibration. What's happening is we're smoothing out the vibration, taking the static out of the vibration, so we're finding that resonant note. So what we're trying to build is a fundamental physics and a fundamental geometry. So we're going to say that somehow or other, and we're still pushing in the direction of this fundamental physics rather than having it nailed down, we're going to say that somehow or other that housing with that inside, middle and outside, that housing somehow becomes a complete unit, and it doesn't need to break down into more complex, say you could theoretically break down the wavelength into any prime number, but we're going to say that the first, the half, the third and the fifth, with the breathing in, breathing out, it all becomes self-contained. So with that, we're going to suggest there's not so much a randomness to, let's say, a fire, as the fire is going this way and that way. We're going to suggest that there's some predictability to the pattern based on this division of waves in halves, thirds and fifths. But we'll get back to that. We're going to look mostly at drawing today. So I've got some pages here. We're going to flip the phone over so that we can look at some papers. I'll do that now. There it is. I hope it's not upside down compared to what my face was, otherwise my video of my face is going to be upside down because the picture is going to have to be up the right way. Anyway, that's what it is. Oops, turn the light on. So this here is what we just looked at, this wavelength here dividing in half, thirds and fifths. And then this is the frame, the 3 nested cubes in the, we're calling it the Great Riddle there. We had this idea of time, times and half a time, 3.5 years of the apocalypse, the period when the Messiah comes and the Judgment Day, all of that apparently happens over 3.5 years, and they say there's time, times and half a time. Oh, one more thing we're going to talk about briefly with this. When we divide the string into this length, we can say that to divide it in half, we need 1, 2. But then if we want to also divide it into thirds, we get 1, 2, 3, 4, 5, 6. We need 6 to divide. So this is equal to 2, 4, 6, and 3, 6. So this is the idea of a 2/3 waveform like that. Not very well drawn, obviously. But this 2/3 and this, the octave here and the thirds here, this is 666. This is the equals 2/3 as a waveform. This was the first clue that I looked at. And so subsequently, just looking at the half and the thirds without the fifth, this one here is equal to 6. This one here is equal to 12. This one here is equal to 24. And so that says there's 24 elders around the holy throne. Each of the living creatures has 6 wings. There's the New Jerusalem is 12,000 stadia cube, and it's got 3 gates on each side. So we're looking at this framework for understanding it, and in Revelation it's looking at halves and thirds, which is the starting point. But then we've also looking at the fifth, and we've got a lot of history there as well, because if we multiply if we look for the fifth here now as well, so we've already got 6, and then we want to take into account this fifth, we've got to multiply it by 5, so everything's got a number. So then this will be equal to 30. So we've got 6, 12, 18, 24, 30. We've got 8. No, we got 10, 20, 30 on the thirds, and we've got 15, 30. So that's the number that you need. So everything's got a whole number. So we got 30 here. So this one becomes equal to 30 if we want to put the fifth on the wave as well. This one here is equal to 60. And so then we're starting to look at base 60 maths, which is a significant component of what we're suggesting here, is that the Mesopotamians, there was a fellow called Atrahasis, the long-lived, very wise Utnapishtim, also called Ziusudra, and subsequently called Noah. That fellow built this ark, apparently, and the ark was a 120, which is this length here, an edge equals 120 cube. So apparently it sunk 2/3 into the water, and it's built on the foundation of base 60 mass. There's a normalized year where if you're looking at a cube as like so, then you've got there it is there. It looks like a hexagon. So that one's equal to 60, 60, 60 going around. You end up with 360 degrees in the circle. That's where it came from. You're looking at 30-day months with a 360-day year. That is the normalized year, 12 months of 30 days each. This is what it says in Revelation, for example, whereby the period of the apocalypse is given as 42 months, 3.5 years, each month being 30 days long, with 360 days in the year. So we're building some kind of clock, and we've used it before because we've got 60 seconds, 60 minutes, the 12-hour and then the 24-hour day. Both are derived from base 60 maths out of Mesopotamia as well. So the suggestion is that Utnapishtim, the great and long-lived, was not building an ark to float animals so much as he was trying to float an idea. And as we just suggested, that's already been very influential, but we're going to try and take it to another level, building a fundamental geometry. So we're going to end up building something that looks a bit like this. It looks a bit convoluted, but we're looking for a doubling pattern through the Platonic solids, they're called. They're named after that crazy, kooky character Plato, who was a geometry mad nut and has also contributed to this idea of a great riddle. So in here we'll see we got a tetrahedron, we got an octahedron, we've got an icosahedron, we've got a dodecahedron, and we've got a cube. So those 5 Platonic solids, and we're going to look at how these are formed through the addition of polar axes. So what we want to do is build up this pattern of a fundamental geometry through, I've done a bit of prep work, build up this pattern of a fundamental geometry through a series of creative days, let's call them. So another contributor to this great riddle, Moses, in his temple design, which he has borrowed from some of Abraham's. He's done a lot of work by himself too, but He's clearly been influenced by these Mesopotamians and by Abraham as well, who also came out of Mesopotamia. So what we want to do is a series of creative days where the multi-dimensional space-time, including consciousness, is created in, Moses gave us 7 days, with the last day being a rest day, and we're going to have a look at how he may well have been right. And he talked about God creating the universe, but it's also about us creating existence as we engage with it. It's happening constantly, this repeating process of creating the vibration pool with which we interact. So we're going to get right into it now. I'm sure I'm going to be ducking back to some of that esoteric background content. But to start with, we're going to look at one line here. So we're going to say this is the center here. This is the source, the original source, and we're going to say it's a bit of light. We're going to call it white light. We're going to say with the first day, this white light emanates out, and it goes into like it emanates out a spherical form. And with the first pole, then we get the first pole here, it's going to be equal to 1 on the radius, and so 2 across the diameter. And so this is all we're going to be doing really in looking at that first one. The first pole, we got 1 dimension, we got, let's call it front back for want of a better, whether it's up or down, I don't know, but here we have 1 dimension in 1 polar axis that runs through the center and heads out. And we're going to start introducing some color theory as well, because we're looking at the way that light breaks down in colors. So we got white light, and here we're going to say it emanates out. There's the first place where the shadow falls, where the light falls, it lands, and it's got a yellowish hue to it on the outside of this sphere. So we can say we've got yellow and white, the first pole. Then we're going to look at the second pole. So now we're starting to get a bit more interesting. Although that first pole is really the start of it all, but they've been called Hashem and Shekinah, the light, the resting place of the light, the masculine and the feminine, the first power, and the feminine what's the word, associate of that light, the light and the resting place of the light. So then we're going to move on to the second fundamental polarity, moving right along. The second polarity, and here we're going to be looking at this thing here called the Vesica Pisces. So this is this shape here, this almond shape here. So we move the circle out 1. So the sphere is sort of pushing out again. We're pushing out. And this point here, if this is it, radius is equal to 1, then this point here, this dividing the space into 6, this origin of that Star of Abraham, the Star of David, that hexagonal structure to existence. We're dividing this space by shifting the circle out, and we're in 2 dimensions here. We've got a flat plane, and this edge, this here, from the center to the apex, is equal to the square root of 3, which is 1.732. But we don't need to know that. We'll just say it's the square root of 3. And this edge here is equal to 3. So we've got the 1 there, the square root of 3 there, the 2 across there, and the 3 across there. But there's another issue going on with this second pole, And here we're looking in a bit more three-dimensional space. Unfortunately, this kit that I've got, you can't build an exact tetrahedron, but this is as close as you can get, but it'll do us for what we need. Tetrahedron, the four-sided triangle, the triangle with the base, triangle base pyramid, and they're equilateral triangles apparently. And so here we have 4. So we got 2 paired poles. They're not going through the middle, they don't pass through the middle, but they're sort of, we can imagine them fluxing around, and where they're going to settle into a particular space, we're going to look at a particular scale to them. And what we're going to find is the distance from the center to this to the vertices, from the center to the vertex, is equal to root 3. So here now we're imagining that these circles are in a three-dimensional space. So one's in front of us, there's 4 on the top, 4 underneath. We get this geometric space is in 3 dimensions, is intrinsically cubic. But we've only got 2 axes here, 2 poles, and these poles are trying to settle into this space that is intrinsically cubic. And so what we're going to find is that the distance that they settle at is equal to the square root of 3, which is the same as it is here. But now we've got a different thing happening. And we've prepped this page up here. So we're going to draw a tetrahedron now. I'll use this smaller ruler. We're going to draw this tetrahedron. I've already prepped up this circle that we're using here. Tetrahedron. With triangle base, we're looking at it from above. And we're going to be careful not to smudge this stuff too much. Try this one first. Looking at it from above here, so these are the 6 edges of the tetrahedron. See that 1, 2, 3 around the top, 3 around the base, 6 edges. We're looking at it, and then we're going to, remembering we're talking about colour, we're going to say that now that first pole we had white and yellow, and now with the second pole we've got red and blue. So, oh, these are red and blue, that's interesting. Lucky, I suppose, but what's happened to yellow and white? Anyway, so we've got yellow, white on one pole, red and blue on the other pole. And so we can say this is white in the apex here from the perspective point, and then there's these call them red and blue and yellow down here. We'll say this there's these 3 primary colours and white formed up in that tetrahedral space. And then what we're going to do is we're also going to draw it in 2 dimensions. We're going to come back here, and if the cube, we'll see it on this cube here again. So this cubic space, this is equal to 2, because this unit cube is the sphere in the side is equal to 1, just touches the edges, so we go 1 in each direction. But this is, we'll get back to, we're talking about this root 3. So we can see that the tetrahedron touches 3 of the corners of the 4 of the corners of the cube. This is the apex, and then there's these ones here. So then there's this. There's 2 tetrahedrons sandwich inside one another. So this base touches with these 3, and this top touches with these 3. So we're building the tetrahedron, and we're saying that the edge of the tetrahedron runs from here to here, to here to here to here to here, and then 3 across. So it's running across the edge of the the diagonal across the cube. And if this is equal to 2, then this is equal to 2 times the square root of 2, this thing here. So then what we have here, the edge of the tetrahedron is equal to 2 times the square root of 2. And this here is, we're getting a true visual reading here. These ones are tipped up so they don't look, they're not to the right scale anymore. But this one across here, we're getting a true visual reading. That's important there. That's equal to 2 times the square root of 2. And that's this length here. So what we can do, using our compass here, we can say that half this length is equal to the square root of 2. And what we know that we can do is if we have this here, I've marked it as the square root of 2, then what we know is that across the cube, across the square, so this is the tetrahedron looked at as a square, here it is here, you can't see it, but when you're looking, because these red and blue ones are not the same length, but when you look at a tetrahedron across its edge, it looks like a square. So this is the square we're looking at. It just touches here, so this is equal to 1 from there to there. And this edge of the tetrahedron here is equal to, so what we're seeing now is a tipped up edge. That's these ones here. The true value is equal to 2 times the square root of 2, which is this diagonal here. That's the diagonal, 2 times the square root of 2. But the visual on them looks like 2. These ones on the visual looks like 2, but they're actually equal to 2 times the square root of 2, which square root of 1 is 1.414, so the square root of 2 times the square root of 2, the square root of 2, 1.414, 2 times the square root of 2, 2.282. 1.414, 1.282, that's correct. So this here, so, and then inside this thing we have this sphere here, this cube, this circle here. We'll draw it a bit darker. This one here is equal to 1, the unit cube, the unit sphere, and we're getting 2 poles, so we've got this 2-dimensional view of an edge equals 2 square, which is a viewing also of a 3-dimensional shape that is a tetrahedron with an edge equals 2 times the square root of 2. And what are we looking at now? So I had something in mind, but I can't remember what it was. So anyway, I won't start on the, I think it was important, but I might start on the, what I'm doing, this one here, this length here, 1, true value of 1. So then we can draw it on here. So this is the first sphere. We're looking at it, that equals to 1. It's not touching there, it's not touching there. Cool. Okay, so that one is the tetrahedron. Then we want to get 3 axes, and we're drawing that one in blue. And with 3 polar axes, we mentioned them earlier, we get, I haven't got an octahedron, but that's what we're looking for. So I'll show you in the cube. You have the 6 faces, and we talked about space being essentially cubic. I mentioned them before, front, back, left, right, up, down. Front, back, left, right, up, down. So these are on the 6 faces of the cube. And so then you have 3 polar axes running through the face. That makes 6 triangular, each of them an equilateral triangle. And you end up with it's a octahedron, which has 8 triangular faces. So it's like a square-based pyramid that is two of them sandwiched one on the other. So you've got a 8 triangles and a tetrahedron. This is what it looks like from above. And so blue, there we are. So this, we talked about 3 primary colours, the red, yellow and blue, which are clearly the same primary colours that I mentioned in the Revelation as the fiery lake of hell, repeatedly referenced as being the red of fire, the yellow of sulphur and the blue of smoke. They're on the breastplates of the 200 million riders of hell who come and slaughter a third of mankind. And they say that everybody who does not have God's name written on their forehead is a natural inhabitant, is a inhabitant of the fiery lake of hell. So we have life as living hell, which is called the second death, which is, we could call it the return to life, but anyway, we're getting a bit, we're still talking about this great riddle, trying to understand. So what we're saying is that if there's a vibration pool, if we're sitting up on the holy throne, then we're in the place of white light. We know what comes and we know what goes, and we're undisturbed by it. So, but then if we're disturbed by what's coming and going, then we're in the what's called the lake of hell. So this is just normal life. And people are attached and they're suffering from pain and karma. This normal life is the lake of hell that they're referring to, and where yellow, red and blue become the foundational structures. So here we are, white, yellow, red and blue. And now what we find is with this octahedron, now we have 6 colours, and they're here on the halfway mark. So this is white, this is yellow, so this is pale yellow. This is red and this is blue, so this is purple. This is white and this is blue, I think, so this is light blue. So we end up with 6 pale rainbow colours. So the idea that there were 7 rainbow colours was introduced by Isaac Newton, who apparently just shone a rainbow onto a piece of blotting paper or something and tried to count the colours, and he came up with 7. But logic and observation perhaps would suggest that he's incorrect, and that there are 6 rainbow colours: red, orange, yellow, green, blue and purple. And here we're looking at what we'd call pale rainbow colours here. The halfway, for example, between white and red is orange, but pale orange. Pale red, really. No, and then orange is between red and yellow. So this is pale red, this is orange here. Yeah, my bad. Okay, so we have these 3 polar axes, and we're getting now these 3 axes in space. So you see this, if we draw a square around here, we'll see that's the middle of it, and then there's an upper 4-sided pyramid. Each of them is an equilateral triangle. We're looking over the face of it. So there we've drawn what we can see of an octahedron. I'm sorry if I don't have one to show you in real life, a 3D model. But then after that, then we want 4 polar axes. We got 3 polar axes. We had 3 days of creation. And then we want 4 polar axes, and what we find with the cube is we've got our 4 polar axes in the 8 vertices of the cube. So now we're going to draw the cube, and we're going to draw it in red. The cube is there's kind of the central frame to this structure that the rest of it hangs around. So we're just going to mark it over here. We're going to maybe try and do it a bit darker because we don't want to lose sight of the cube when we come across the icosahedron and dodecahedron. And we're going to also look at the cube octahedron as being the final resting day. So we got this hexagonal view. Oops, we forgot to draw the I'll go back to that. We forgot to draw the octahedron on the square shape. Cube. This is cool. You can be drawing along, everyone. Pause it up and draw it. This is a great thing to do. All I've done here is I've made a circle, and then I've divided it using the same length as the compass. You divide it into 6 even parts. And then I've divided these 12 here as well by little cross from here to here. It gives us half this length, so then you can draw these. I divided it into 12 because we'll need that a bit later. Cube, nice and bright red. And we're going this direction. There we have a cube. And we're just going to duck back here for a second. We got it in blue, but then we're going to find that blue. We're going to find that the cube octahedron, sorry, not the cube octahedron, the octahedron touches the centers of the cube octahedron also, because this one is running across the diagonals of the cube face. We find that the octahedron touches the center of each of these tetrahedron edges, like we showed you on the other picture actually. So it's going to look like this. So this is going to be a thing, and it's going to be shaped, sloped up to the center point there, and that is going to be a little octahedron. And then drawing the cube on here, the cube is 2 by 2. We already have it. We've got it in green, but we're just going to leave it like that. So we've got the cube here, we got the cube here, we got the tetrahedron in green, we got the octahedron in blue, we got the unit, circle or sphere. And so once we go here, so we got 4 days of creation now, right? So we've divided this space. If you think about dividing this space here into the front, back, left, right, up, down, then what we've got is 8 cubic spaces. On the top left up, top right up, bottom right down, etc. You got top right up, top left up, top back right, etc. I'm not sure I said all that correctly, but you get the picture. 2 times 2 times 2, dividing that space into 2 to the 3 makes 8 spaces, 2 to the power of 3. So then we start getting a bit more complicated. We're looking to do 6 dimensions, and so far we've got 2. So what we need to build now is a dodecahedron, And because I built the icosahedron here, then I was only able to build this half a dodecahedron with the thing that I've got, and I can hardly show it to you in this picture, but it's got 12 pentagonal faces and 20 vertices. So on our cube we've got 8 vertices makes 4 polar axes. Here we got 2 polar axes. With the octahedron we got 3 polar axes. So we're theoretically looking for 5 polar axes, but on the dodecahedron we've got 10. But we're going to be, so what we're suggesting now, remember we're trying to fit it into this broader pattern like this. So we got the 64 spaces, and with this central cube here, we're saying that it's stable. So then we're looking for the field around the cube. So we're saying that the cube shape is more stable, but that the field involves the shifting and changing, and so the shifting and changing is embodied in the dodecahedron and icosahedron. So these are days 5 and days 6. So the way that we draw a dodecahedron, and I'm going to show you something, and this is not the way to draw a dodecahedron. This is a very popular method for drawing a dodecahedron based on something called the flower of life, or the Metatron's cube. Because you can see this is a pentagon and it's tilted up here. This is how you can see it's everywhere on the internet. People build dodecahedrons like this all the time, but it is clearly incorrect because this pentagon face here is tilted up, and this one here is tilted up but at different angles. But this distance across the shoulders here, A to B, needs to be the same, and it is miles off. So if you're a student of geometry, and hopefully you are, then I will show you a very simple method for drawing a correct dodecahedron, but not only a correct dodecahedron, but one that is a fundamental dodecahedron, the first dodecahedron, which neatly wraps around the cube. So this here, we know from here to here across the diameter of this circle is equal to 2. And we know that the true value of the shoulders across the dodecahedron, I'll show you a correct one rather than the incorrect one. The true value of the shoulders across the dodecahedron, that's the other view. Here we are. So this dodecahedron here, the cube fits inside the dodecahedron. And see, it goes here, we can see here going across the face from edge to edge across the pentagon there. So there's another face of a dodecahedron. Here's one, and there's the cube face. So the dodecahedron has 12 faces and the cube has 12 edges. So the dodecahedron fits around the cube, neatly around the cube, with the cube taking up 8. So this is equal to 2 here. So what we can do is we're just going to use that to our advantage here. We're going to say this is a true value of 2. As you've seen with the dodecahedron here, we want a true value of 2 from here to here, because it's just tilted up. It's a true value. As compared to this edge of the cube that we're looking at here is tilted. So it's not, the visual reading is not the correct value. So we're using this true value here of 2. We're starting at each of the points here. We're going to mark them around the circle here. Each of these is equal to 2. Hope you got your paper and pencils out. So we got 6 of these spots. And then we're going to draw the edges of those, and we're going to use the black. I'll just use this black, and I'll just use this little ruler, and we're going to draw around the outside here, and then I'll show you how to draw the inside part of it. It's very easy. black around the outside, a dodeca. The iconic dodecahedron. We'll join up the dots about there. This one here, we've got to be careful to get it in the right spot, otherwise it's going to look dodgy. This is the fundamental first dodeca wrapped around the first unit cube. And so, as we were saying before, the vertices of the cube from the center are equal to the square root of 3. And it's the same with the dodecahedron. And that is useful for us. I'll show you why. We end up with a very strange little problem. Oh, and we're talking about fifths, of course, when we're talking about the 5. So far we've got it's like the numbers are built into the geometry as well. And the way that we're looking at them is also, they make sense because we look at them. The way that they manifest their most obvious shape, such as with a hexagon or with a square, is because we're looking at them. And then when we look at them, they make sense not just in terms of the shape, they're comfortable and rational with one another because of their being looked at. Hang on. All right, so we're talking about 5s, right? So we got this number phi, which is 1.618. I'll write that on there. 1.618034 to be precise. So what we have here is this classic Fibonacci sequence, and this number is tied into anything relating to pentagons. It's built into the structure of life, so it's a growth thing. So you could say, generally speaking, this section here is equal to 1, then this section here will be equal to 1.618. And if this section is equal to 1, then this section is equal to 1.618. 1 is to 1.618, 1 is to 1.618, 1 is to 1.618. It's all through the manifestations of nature because it's a growth pattern. So the Fibonacci sequence is 1, 1, 2, 3, 5, and what you're doing is you're adding the numbers. 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13. And as we go along the progression, so 5 plus 8 is 13, then we go 13 plus 8 is 21, and we'll try it here. 21 divided by 13 equals 1.615. It's getting close. 1.615, not sure if you can read it. But as we go further along that progression, we come closer and closer to this irrational number, which is called phi, and looks like that. And how we find it is we've got root 5 here, and we're using the same rule we had before, the Pythagorean rule. That's a square right angle. This is a rectangle here. This is equal to 1. This is equal to 2. So the square on the hypotenuse is equal to the sum of the squares on the other two sides. So the square of 1 is 1. The square of 2 is 4. 4 plus 1 is 5. So the square root of 5 on the diagonal. So we find that we want the square root of 5 plus 1. So this is the square root of 5 plus 1. And then we divide it by 2. So we get phi here. So that's 1. That's phi. So it's proportionally harmonious. The relationship of this proportion to that proportion is the same as the relationship of that proportion to that whole length. A is to B as B is to A plus B. So that's how it works. It's a beautiful thing. So if we divide 1 by 1.618, we end up with 0.618. And if we divide 1 by 0.618, we end up with 1.618. That's the only thing it works for. It's called the golden section. It's got a few names. We call it phi. And here we've built it, and so this phi number is built into dodecahedrons and icosahedrons, which icosahedrons also got the 5 pentagonal structure. But now what we're going to do is we're going to finish drawing this dodecahedron. So we started with this 2, true value of 2 across here from each of the hexagon points. Now we've got some kind of augmented hexagon. Now for each of these little areas, I'm going to go here and draw a very light parallel line. I'm going to duck across here. I actually haven't done the maths to check if this touches here. That's bad of me. We're going to duck across here. If I've done it, I've forgotten about it. So we're parallel to there. We've got this point to this point. And here we're parallel to that one. Here we're parallel to this one. Here we're parallel to this one. Finally, we're parallel to this one. And what we're going to do is we're going to mark some spots. We're going to be marking them over here. And we're dividing this line in half here. We're going to mark it here. And we only want 3 of them because we're only showing the top part of the dodecahedron. We're not going to be looking at the back. So we're going to skip one and skip one there. And we're here, so we're in the center of this line here. And then what we're going to be able to do is with our black marker, is draw these pentagons. So this one's here is tilted up like that. This is one pentagon. And then this mark here, back to here. The third one here. So this is a very simple method. I would say the simplest method, and I devised it all by myself, and there doesn't seem to be anybody else drawing it. But it is very simple and it is correct. So this one here in the black is the dodecahedron. So I was guessing a bit as to which colours are going to make it look best. So what we're finding here is, so this is a pentagon here, sloping up to the centre point where we're looking down on it from the centre point like so. I can't even fit this thing in there. We're looking down through there somewhere. That's not even the halfway mark. We're looking down through one of the 10 axes here. So we've got 3 pentagons, 4, 5, 6 pentagons visible on the top. The other ones we could mark them here and draw them in behind, but we're not going to because we're keeping space. I wish this were a bit darker, but we're going to look a bit at the pentagon because we've got a beautiful thing going on for us. And this line here, for example, you see how this cube edge is running across this face here, and then this cube edge is running across this face of this other pentagon. Then what we have here is this line here is parallel. It's floating up in the air, but it's parallel to these two. It runs parallel through the center of the cube. So that's great for us, and what we find is that this is the square view here. So what we're finding is that this edge here is equal to 2 divided by phi. So the answer to that is root 5 minus 1 is 1.236. So that is on our paper, wherever it was, this one here. We've marked this already. So this is this one here, root 5 minus 1. And then, yeah, because we've got this thing here, whereas if we multiply 2, we got 2 here, 2 times phi. 2 times phi equals root 5 plus 1. And 2 divided by phi is root 5 minus 1. These are in a phi relationship with one another. 2, root 5 minus 1, and root 5 plus 1. So this shape that we've got here, we're going to use it. And we're going to see that root 5 plus 1, root 5 minus 1, sorry. This is the edge of the dodecahedron, and the vertices edge is 2 divided by phi is root 5 minus 1. Excuse me, I'm just trying to remember how I'm drawing this. Oh, yeah, and the distance from, where are we, here to here, what we've got is 3 rectangles that run, so this cube takes up 8 of the vertices of the dodecahedron, so the remaining 12, sorry, we got 12 remaining vertices. There's 3 rectangles that run through the cube in the 3 fundamental directions. So this one here is root 5 minus 1. This edge here is equal to root 5 minus 1, but the not drawn long edge of the rectangle is root 5 plus 1 because it's multiplied by phi squared. So on here we have the edge equals root 5 minus 1, but the root 5 plus 1 is that long edge. So we're going to get this one here, this length here, and we can mark it on here like this. These are 2 of the points of the dodecahedron. And then we've got this square up here as well. That is approximately correct. And so then we can mark this little square here. I'm just going to guess at it because it doesn't, I'll do this one actually. I'm just guessing at it. Drawing that across there like so. The ruler here gives me a visual on these other ones, so pretty close. This is just a marking line. So we're just saving a bit of time just guessing at this one. So, and then this square down here passes through our mark approximately. Yes, it does. So this square that we've drawn is root 5 plus 1, which is 2 times phi. And then we want this root 5 minus 1. Oops, we need to divide it in half. We'll just do that quickly. Divide this line in half like this. Oops, it's a bit big. There, and root 5 minus 1. So this is half of root 5 minus 1 is here. We need this one because this is the width of the edge. This is the edge of the dodecahedron. So then we can draw it, and we're drawing it in black. This one here, that's one of the edges. This is now we're looking vertically down on the dodecahedron, just touching this vertical edge of the cube is span, so this is one of the vertices of the dodec, and then it's vertical so we can't see it. And the vertical edge of the cube is spanning across the face of this as well, vertical, and this one, vertical pentagonal faces of the dodecahedron, just touching there. This one's an actual edge. And then this one here. And then we've got a edge that's visible up to us here from on the center. This is the same edge still. And this one we'll draw it in black just beside the blue there. And we're going down here this way. I seem to remember I did the maths and that this one lines up with that one. So I'm going to do it because it's obviously, I remember it, although I didn't check it in preparing for this. So we got these pentagons. Yeah, I'm absolutely certain that lines up there. This point with this corner here. So here we can see 4 pentagons leaning up, 2, 3, 4, and this is the square view onto the primary dodecahedron. And then after that, what we want to draw is alright, so what we're looking at here again, this is a rectangle, this is 2 times, this is root 5 plus 1, and that is 2 times phi, so the edge multiplied by phi, and this edge of the dodecahedron is 2 divided by phi gives root 5 minus 1. So we get these phi relationships and we get this beautiful hexagonal view of the dodecahedron here. And we mentioned we've also got this pentagonal view that we're not going to draw, where we're looking at 1, 2, 3, 4, 5, 6 of the 12 dodecahedron faces. Forget about this icosahedron for now. But these 6, and I've just drawn it in pencil here, I'll draw it again. Now we see the cube tilted up this way. The cube's not, we don't get a, so this line here like this. Here, and then across here. I already marked it gently, but this here is the cube tilted up like this. So we're seeing a phi relationship between this and this. This is not a square. This is tilted up on an angle. And then this, yeah, so that's in a phi relationship. And you can see how the cube, if we hold the dodecahedron still, then we can see how the cube fits 5 different ways into the dodecahedron. We can tilt it this way, we can tilt it this way, we can tilt it this way, and we can tilt it this way. So we got 5 ways that the cube fits in the dodecahedron. But what we're doing is we're holding the cube still, and we're saying so again we twist it here. So with here, then we twist it. So we keep that still, then we'll twist this around. Unfortunately, don't have a dodecahedron to show you this. We show you on the icosa how it works. But this one here, you see this again. We're getting these rectangles through the 3 fundamental 3 polar spatial directions through the icosa, and then we twist it on any axis, and we end up back in the same place. But so with the dodeca here, you twist it on any of its 10 axes, and you come around to resting back on the corners of the cube. And so then, but what we're going to see here now as well is, so that gives us 5 positions for the dodecahedron. But you see how this one is oriented parallel to these lines. What we could do is build the dodecahedron on this other side, augment the hexagon on the other side, and then you find this line here is twisted around the other direction. So you get 5 orientations on this, with this 5 positions with this orientation, and 5 more positions with that orientation. So you end up, this is related for sure. I don't know, there's a mystery in there for me somewhere, but looking at how why the 5 polar axes of the 5th day has turned into 10, it's somewhere here in how it splits in half. But then what we can do is, if we're looking at which edge of the cube is joined on to which position of the dodecahedron. So the dodecahedron's whizzing around in all these different ways while the cube is like stable in the middle. We're talking about a field here. So we've come up with 10 positions, but then there's 12 edges on the cube. So depending on which edge of the cube is in which position, there's 120 different orientations for the dodecahedron around the cube. And we remembered we're talking about this situation here amongst what we're talking about. This is equal to 120. That's the edge of Utnapishtim, Noah's Ark. So we're talking about, we're still manifesting some kind of fundamental existence. So we can't see 5-dimensional space. So this 3-dimensional space with the octahedron here, we're looking at spatial, the space with front, back, left, right, up, down. Then with 4 dimensions, we're going to add in time in the cube. So we're already can't quite see what's happening. It's kind of outside of the cube is like a reflection of the deeper reality, which also houses time. But then in 5 dimensions, we're again further away, and we're looking at, now we suggested, growth and decay. And with those 5, then so we could also look at 2 to the power of 5 now is 32. So 32 is, then we're getting back to the Sefer Yetzirah, which is the work of Abraham. It says in the text it's the work of Abraham, although people have trouble dating the text to then. I can't see who else would have come up with that literature. We had the construction of the Hebrew alphabet in the Sefer Yetzirah. I'll write it here for you because it's going to be upside down, isn't it? Sefer Yetzirah. It's going to take you like 20 minutes to read it. It's find it on the internet. And what it does, it builds the Hebrew alphabet in parallel with a geometric cosmology. So it begins, remember our tetrahedron here. So it says there's 22 letters, and there's 3 mother, we're starting with God, and then we say there's 3 mother letters, and those are described as yin, yang, and balance, effectively. And then we end up with 7 double letters. So God is then placed in the middle of the cube. So 3 mother letters, God in the middle of the cube, and 6 polar directions in space, up, down, front, back, left, right. And those are the 7 double letters. And then there's 12 ordinary letters. And then we can look at the 12 in relation to the dodecahedron and the icosahedron and this other thing that we're going to draw, the cube octahedron, which touches on the centers of each of these edges. This is what Abraham described, the cube octahedron, which we have. I built this one. So we look at it this way, it looks like a hexagon. but then we look at it this way and it looks like a square, because what we've done is we've cut the corners off. It was a cube, we've cut the corners off. Like this on here, we cut the corner from here to here, cut that corner off, and we end up with a called a cube octahedron, which has got these 8 triangular faces which were in the corners of the cube, and these 6 square faces which were on the faces of the cube. And each of these vectors is equal to the square root of 2, because this is equal to 2 across here, and so this is equal to 1 from here to here. So this 1, the hypotenuse is equal to the square root of 2. And the beauty of this shape is that the distance from the center of the cube to any of these vertices again, from here to here to here to here, is also equal to the square root of 2. So we have, Buckminster Fuller called it the vector equilibrium, and it is a significant shape in the structure of existence, and it's significant for us as well. We're going to call this the 7th day, the resting day. And we're talking about colours, right? So Abraham has given us these 22 letters, but here we're talking about 22 colours as well. There's obviously a direct parallel. So we've got the 3 primary colours with white, red, yellow and blue, and white makes, well, let's start with the 3 primary colours. And then we got 6 rainbow colours with God in the middle. God's in the middle is white, and then we've got 6 rainbow colours on this octahedron. So then that's 7. White and 6 rainbow colours make 7. And then we have 12 crystal colours. And these, there's the 12 ordinary letters. And these 12 ordinary letters are described by Abraham as being on the 12 edges of the cube. But there's also reference to 12 crystals in a couple of significant places, where we had, for example, the New Jerusalem that the Messiah is ushering in, the great global peace with the one religion or whatever it is a 12, this is edge equals 12,000 stadia. It's massive, and there's 3 gates on either side of this cubic perfected city that's floating down from heaven, apparently. And so we get this, the colour theory providing a direct parallel to the structure of the Hebrew alphabet coming from the Sefer Yetzirah. And we see it in relation to this geometric cosmology. I don't know that Abraham knew about icosahedrons and dodecahedrons, but Plato certainly did. And they're Platonic solids. So we'll get back to drawing that cube octahedron because it's significant. But we're looking at the dodecahedron here at the moment, how it's whooshing around this cube here, and there's 120 orientations for it. So then the next one, when we got 6, is we've got the icosahedron. 6 axes, and now we're back to 12 vertices, gives 6 polar axes through the icosahedron. So again, these we can look at these edges here. This, you can see it here, these where my fingers are, makes a rectangle left to right, and this one here makes a rectangle up to down, and these ones here make a rectangle front to back. You get these 3 rectangles running through the geometric space, and again these are in a phi relationship. And this time in this one here it was phi squared from the edge to the long run. This one is just phi. And this one, we're going to draw this icosahedron in a way that it's not normally drawn. What we've drawn here is pretty standard sacred geometry for how these cubes how these shapes naturally nest. They nest one around the other in relation to one another. But then people generally put the icosahedron outside the dodecahedron because they're pairs. They're a pair to one another. So if we join the centers of each of the icosahedron's faces, you see you get a pentagon at the top here, and so you can continue around and you get a dodecahedron. And likewise with the dodecahedron, on the center of each of its faces, if we join up the centers of each of its faces, you'll get an icosahedron. So what's normally done is people put the icosahedron outside the dodecahedron, but that results in a tripling in size because the dodecahedron then fits on the tetrahedron again, fits inside the tetrahedron. But like this. So this orange icosahedron that I've drawn, it touches at the apex of this bigger tetrahedron. I'll do it on this side. There's the apex there, and then this one here, and then it divides this line here into a phi relationship between here and the apex. So, and likewise these three corners, this one divides this line into a phi relationship, this one divides this line, and this one divides this line into phi relationships, and the face of this icosahedron is lined up with the face of the tetrahedron. But the way that I've drawn it here is with the doubling in size, which is what we're drawing now, but most people draw them bigger, resulting in this tripling in size, which is less fundamental because doubling is a more fundamental pattern. So then how we draw it, again, get your pencils out. We need these little marks here because we're happening in parallel with the dodeca. The icosahedron is in parallel with the dodeca. Not parallel, that's ridiculous. They are to some degree related to one another. They work together, defining the field. They work together in defining the field of of the manifest form, which is this multi-dimensional. Sorry, that goes there. That goes there. So then we can draw this hexagon, and we're drawing the icosahedron. We got purple. Yes, purple. First we got a hexagon. We're looking at the hexagonal view again. So this is a pentagonal view. But when we look through the face, we get this view of a hexagon. So we're getting the view through the face of we got through the vertex of the dodecahedron, but we're looking through the face of the icosahedron. And this is the pentagonal view. Like I showed before, we can also look at this is a hexagonal view. Like I showed before, we can look at a pentagonal view of both an icosa and a dodeca and how they interact together. We'll look at that again. But this one here, where we're joining it, we're touching on the, I hope I'm drawing that on the right side. I'm sure I am. Because I've drawn the dodeca on the right side, so if you draw it around the wrong way, it goes funny. But I think I've got it right here. That's the hexagonal outline of the icosahedron. But this point here where it's touching on the cube, it's not actually touching in space. That's what we're saying again about how how the icosahedron, so yeah, it makes sense because we're looking at it. It divides this line into a phi relationship. 1 is to phi, all of these, 1 is to phi. But it only works visually in three-dimensional space. This icosahedron at this scale is not touching those places. So then we get this point down here. Where are we? We're on the... We want to also divide here this tetrahedron. And then we got this. So again, it doesn't touch the tetrahedron in 3D space, but visually it does, because we're looking at it, it makes sense. This the part of the incredible beauty of geometry is that it reflects some true majesty in existence. Here we're dividing the tetrahedron again. Here. It's starting to get a bit murky on the page, and that some purple's gone a bit wrong for us. So we're drawing there's 20 triangles, 20 equilateral triangles go into making up the magnificent icosahedron. That was a bit of a wobbly one. We've got to divide this line again. The point here. Tetrahedron. So 5 relationships on the tetrahedron. By relationships on the cube. So this on the tetrahedron here, this is equal to 1 is to 1.618, or 1 is to 1.618 squared. So then we've got the visible face here. Face we're looking through this triangle on the top. This one's gives us a true visual representation of the triangle. True value, these lengths, this edge here is the actual edge length of this magnificent icosahedron. So as you can see, we've got a bit convoluted in that picture, but we break it down into these 6 fundamental polarities now. And we're going back here. You're doing well. We're doing well. You pause and have a break if you want. But now we're going to draw this icosahedron on here as well. Or will we bother? Maybe we should just show you a thing. We're getting a bit long. Here we are. Yeah, we'll just do it here. This is all right. So this one here, you see this 4 divided by phi. The edge of this whereas with the dodecahedron in the black, the edge is equal to 2 divided by phi. The edge of the icosahedron that we're looking at here, this is the true value of the length, is equal to 4 divided by phi squared. And that, 4 divided by phi squared, is equal to 2 times root 5 minus 1 divided by phi. So that equals, should have written the mark there. Oh, that's the length of it. I measured it up for this purpose. 4 divided by phi squared, I've divided it in half. Now we've got to figure out how to draw it. Looks like I'm drawing it. So that's the true value. That's a true value there of the icos's edge, which is 4 divided by phi squared. So we'll go here. here, that's the true value of the icosa's edge. And we've got them out here as well. 4 divided by phi equals, is on, oh, I didn't mark this one, 4 divided by phi, it might be root 5 plus 4 divided by 1.618 equals 2.472, which is 2 times root 5 minus 1. So 2 times root 5 minus 1. So we're going to be drawing a square. We'll mark it in here, over here, I've actually already marked them. How cute. So we got this little square here. If I still had a pencil, it would be good. This is just the setting out marks. So we've got this purple here. This is the icosahedron's one of the edges that with the rectangle of one is going through this direction, through the thing. And then this now is going back to 4 divided by phi squared out here. You get 2 more edges, they're purple. You there, you there. And then we got the center mark out here because this one runs this way, this rectangle runs this way. This rectangle runs crosswise, this one runs down, this one is vertical and runs this way, so then we can join up these, but we can join up another one as well. Join up these, and we can join up these. Join up these. We join up this. No, that one doesn't join up. This one does. Whoops, we're getting murky with purple again. And goes that way. And goes that way. This way. And here we're going to get the icosahedron. What view do we call this? It's some sort of the square view on the cube. So we've seen that the dodecahedron can have those rectangles can be oriented one way or the other. There we have the icosahedron. Here's the view of it like this. Here's in the purple here, this is what it looks like here. And this one here visually doesn't line up so well, but you see this one here lines up like an absolute beauty, dividing the line of the cube and the line of the tetrahedron. And we can see this one here, this is drawn at the same scale again, whereby this I've done this maths. This one is perfectly touching in that spot there. This icosahedron here, but it's perfectly touching, but again, not in 3D space. This is visually lining up. And there's other things that line up here. The way this wraps around this is truly beautiful. so that you can draw a circle around here like this. I should draw that one really, but anyway, we're not. You'd be happy to know, I'm sure, because we're up to 1 hour 30 and we're coming to an end. So this one here, just to reiterate, the icosahedron was looking at these three orientations. There's three rectangles running through the 3D space, but then we find that again we can orient it that way, and that gives us 2 times, and there's 30 edges, there's 5, there's 10, there's 20, there's 30 edges. Each of these, so again we're back to 30 with that we saw out of the Mesopotamian stuff. We're going blurry for some reason. I don't know what that is. Hope we haven't been blurry for too long. That's not great, is it? Oh, it likes it really close up, doesn't it? No, that's going to be annoying if it's blurry for too long, but I'm sure it was focused before. Anyway, we'll have a look back. Okay, so this one, maybe I was doing some weird stuff. I focus on that phone. Nah, blurry. Anyway, so yeah, the final thing I'm saying here is that this thing here has got 30 edges, and then it's got 2 orientations, this way or this way around the cube. Then now, depending on where these 30 edges of this icosahedron goes, you get 60 possible positions for this icosahedron around the 60 possible positions for this icosahedron around the cube. And again, you can tip it on any one of these axes, you end up in the same place. So these, maybe if I try this for a bit. So these 6 axes, this geometry is reflecting of a deeper reality. We're saying that we can't actually visually encompass the 6-dimensional existence, but it's reflected in the geometry, and in the same way that 2 by 2 by 2 makes 8 spatial areas, then we find 2 to the power of 6, we find another harmony where there is 64 spaces. So we see them in, assuming we're getting some kind of focus going on, focus. That one there, 64 spaces with the fundamental geometry inside it. So we're getting the spark, the form, with this is the cube, the central cube that we're talking about, base 60, and then the field around the outside of it. And we're looking at the way that waves flow in. So it would be great to build a wave pool. Because seems to me that if we can build a wave pool, then we can build something that is able to resonate with the far distances of the galaxy would be ideal. So we got this potential scope on how to build a space travel machine, for example, something that resonates, so produces energy, something that we can read what's happening, we can look at what's happening in real time in distant locations. It's all a bit pie in the sky. I don't know how to do that stuff, but it seems to me that this is the lens we should be looking through in trying to do that stuff. And we're going to revisit again just briefly in our minds. I'm going to check this again. Focus is dodgy. Wonder why. Yeah, I'm probably out of focus too. Who knows? But anyway, Utnapishtim, the Noah's Ark, 120 edge equals 120 cube. There's a 30 and a 60 within. There's the waveforms. It's built to show the fundamental patterns of nature. What we have not looked at on this geometry is the cube octahedron, where we join up the 6 edges of the cube, and we're not going to do it now because the blurry thing. I'm going to put this video up anyway, even if it's blurry. Okay, I think we covered most of it, and have a great day. Thanks, bye.